Back. Hope you had a good break. And now we're going to reach the top of our three-step journey. And we're going to do this by talking about something called the adjoint. The adjoint is going to give us a deeper understanding of what the transpose means and give us a very natural reason for why the eigenvalues of a linear map should be equal to the eigenvalues of its transpose. And here we don't need to talk about polynomials, we don't need to talk about determinants, we only need to talk about what the transpose means. So let's start by talking about what an adjoint is. Before that, we need to introduce the dot product or the inner product. So the dot product, you might know from working with vectors and geometry. And instead we're going to work with the slightly more abstract inner product, and it's going to be denoted U product V. And the dot product, or you could think of this as just the dot product, but depending on which coordinate system we're working with, we could define different kinds of inner products that all have essentially the same properties as the standard dot product. Okay, so we have this dot product to work with, this inner product. Let's begin. So the adjoint of F, which I'm going to write as F transpose, is the unique linear map such that F of U dot V is equal to U dot F transpose V for all U and V in the vector space. So these two, this is quite interesting that there's a unique map where this is true. And the motivation for thinking about all of this is it's a different story. But the main point is about duality and how is it that every kind of a special kind of linear map can be written as an inner product expression that looks something like this. Okay, so I write this adjoint as F transpose because it turns out that the matrix of F transpose, of the adjoint of F, is exactly when you transpose the matrix of F. So then, actually, F transpose is exactly the adjoint. The matrix and the abstract version match up exactly. Okay, so let's do this. Let's try to show that the eigenvalues are the same. First, let U lambda or lambda U be an eigenvector eigenvalue pair or eigenvalue eigenvector pair of F, and consider this expression we had, FUV. So first of all, we could evaluate this in two different ways. The first is by using the definition of an eigenvector, which is that while applying F to U is the same as scaling it by lambda. And I'm going to rewrite that slightly by pulling the lambda out from the inner product and then putting it back into the second slot. Oops, yeah, there we go. So now we're only dealing with the second slot. And we want to deal with the second slot because the transpose is something that comes in from the second slot. Let me rewrite what just happened. Fu dot V is equal to U dot lambda V. And it's also equal to, by evaluating it in a different way, U dot F transpose of V. Because the transpose could move across slots for any vectors that we work with. Okay, so let's set these two equal to each other, the two different evaluations. U dot F transpose V is equal to U dot lambda V. Now we're going to subtract the right-hand side from each side. And the reason we do this is because these two inner products can be put together since they have the same first term. And inner products have a property called bilinearity. So what that means is, since the first slots are the same, we could, in a way, factor out the u from both sides and have the second slot combined. Okay, now we factor out the inside and look at what we have here. This map, F transpose minus lambda I, is exactly the map from part 1 where it tells us, this one is intimately connected with the eigenvalues of F. So if we could show that the kernel of F transpose minus lambda I contains a non-zero vector, then that means that lambda is also an eigenvalue of F transpose and will be in really good shape. So let's just pause and appreciate this, that we've used basically nothing, and we've come up with an expression that looks really connected, that really connects the eigenvalues of F and F transpose. Let's take this a step further and see what happens. So we need to show that the kernel of F transpose minus lambda I contains a non-zero vector. And the way we could do that is by showing that there is something in the vector space that the second expression cannot hit. What I mean by this is that V is free for us to choose. So if we vary V, its image under F transpose minus lambda I could be a variety of different vectors. Yet this expression is constraining that. It's saying that whatever the image is, when it dots with U, it must vanish. It must go to 0. Okay, so then we could think of a special case. This special case is very cool, which is that there is no V such that F transpose minus lambda I applied to V is equal to U. Because if that were true, then our previous expression would reduce to U dot U is equal to 0. But this cannot happen since U is non-zero. We might think of this is the positive definite property of the inner product or the dot product. Or another way to think of it is when you dot a vector with itself, that is computing its length, which must be strictly positive if the vector is non-zero. And here we're saying that a non-zero vector's length is 0, which is a contradiction. So there is no V. So U is not in the image of F transpose minus lambda I. Now, we could do a variety of different equivalent linear algebra approaches to show that this implies the kernel of F transpose minus lambda I contains a non-zero vector. I think the most straightforward, once you understand what's going on, is to use the rank nullity theorem. Since the image of F transpose minus lambda I is not the entire vector space, because it doesn't hit U, it cannot be full rank. and so its nullity must be greater than 0, and so its kernel contains a non-zero vector. And concretely, this means there is a W where F transpose minus lambda I applied to W sends it to 0, which means W is an eigenvector with eigenvalue lambda. Okay, so we're almost done. That means that any eigenvector of F is an eigenvector. Now, any eigenvalue of F is an eigenvalue of F transpose. And any eigenvalue of F transpose is an eigenvalue of F if we apply the argument but replace F with F transpose. So we do the same thing but like kind of on the other side. It's symmetric. The argument is exactly the same. Since the transpose of F transpose is F. And so they share eigenvalues. But hope you appreciate this. I really appreciated it when I first saw it. This gives us a really, really pretty way of doing this. And I think it was worth looking at the two other approaches too. And those were steps along the way of, understanding this result. Why are the eigenvalues the same? The two other ways give us two different perspectives and some loose ends to think about. Like, why is the determinant of a map the same as the determinant of its transpose? What are really the relationships between polynomials and linear maps? And how come the adjoint gives us such a good understanding of what the transpose is? Well, I hope you have a wonderful time, and I will see you next time.